diffusion
না
drift current কাজ করে তাই it's a function of velocity
ये ना कुछ
diffusion
प्रॉब्लम है कहीं सीनियर बोलता हूँ चेक करो जो भी आ रहा है
I को देखি diffusion এর equation
हम यार अगला साल हम लोग चेक करिए
confidently বলে দিতে পারে আজকে সেকেন্ড রাউন্ডটা ওখানে কি দিল
बस यार हम लोग फ्री में पैसा देता उसने हमारा अभी 31 तारीख से पहले बुलाइए एक बार एक लोग
পরে মানে ও সব জানে কিছু কিন্তু ব্যাপারটা অলরেডি
और वो 12,500 में बात 12,500 वो अगस्त से शुरू हुआ लेकिन डिस्कलेशन हो जाता है कि एरियर आई सब मिला के एक साथ
ডায়োড আমি বাপের জন্য শুনি ফরওয়ার্ড বায়াস ফরওয়ার্ড
ठीक
ডিফিউশন
बोला था
ফরওয়ার্ড
दे
বায়াস
हमने
তাহলে ডিফিউশন কারেন্ট
फिर तुमने सारा एलियन खाना बोलत के नहीं हां
ড্রিফট করে ইলেকট্রন অলরেডি ইলেকট্রন সেট ফিল্ডটা ছোট ছোট
ডিফিউশন কার মানে তাহলে মাইনরিটি কার
হ্যাঁ আর ডিফিউশনটা করলেও করে
রিভার্স বাইসে যে লিকেজটা দ্যাট ইজ একটু
আর
ডিফিউশন
ডিফিউশন হলে সেটা টাইম ডিপেন্ডেন্ট কারেন্টের প্রোফাইলে টাইম ডিপেন্ডেন্ট হবে ইকুয়েশনটা টাইম ডিপেন্ডেন্ট হায়ার থেকে লোয়ার কনসেন্ট্রেশনে যায় লোয়ার থেকে হায়ার থেকে
হায়ার
লোয়ারে
থেকে
যায়
লোয়ারে যাবে
ফিল্ডের ওপর ডিপেন্ডেন্টই না
আর উইডথ অফ ডিফিউশন যেন
হ্যাঁ তাহলে তো ফিল্ডের ওপর তো ডিপেন্ডেন্ট হলো কি করে
ভোল্টেজ আই থিঙ্ক ও কি কনফিউশনটা করেছে বলতো ও ভেবেছে যে ফিল্ড উইডথটাকে কি বলে ডিপ্লিশন উইডথটাকে তো ভোল্টেজকে তো ভ্যারি করাতে পারি এবার ওটাতে ভ্যারি করেছে এবার ওর এটা মনে আছে যে ডিফিউশন কারেন্ট ডিপেন্ডস অন দ্য উইডথ অফ দ্য ডিপ্লিশন রিজন করে ও ওটা বলেছে
সিনিয়র এগুলো
বলবে একটু যান পিকেবির বুক ক্লাস করে আসুন যান don't talk about such thing in with VR now people.
Okay, so good morning. Let me share my slide first. Yeah. So I hope my slide set is visible to all of you. Is it fine?
Yes, sir.
Okay, thanks. Uh, so we discussed, this one of the algorithm for finding out a hypothesis. Hypothesis given, as I mentioned, some of the training examples in the form of Boolean literals. When we can, so hypothesis in the form of Boolean literals, and in the training examples, we provide it as a description of certain attribute sets, and we represent them as a vector of attributes. So, and this algorithm, we named this as find S, which means it is finding out the most specific hypothesis uh, of the training given that training example. So the idea here is that when you are finding out a hypothesis and you are assuming that your training example should not have any error, that means all the training examples, they're true, there is no error. So your assumption is that at least what you are trying to satisfy with respect to your hypothesis, that all the training examples should be true with your hypothesis. That means in your hypothesis, which are positive examples, training examples, that should be accepted because it's a Boolean expression. So the final outcome would be true value. And if it is a negative example, then given that input, your functional value should be false. So that is what here you can see that in your representation, H is a hypothesis and X is that input. So the output what you get from the hypothesis, and C is the target function, which means hypothetically a true target function, it exists, and for that target function, at least this property would be satisfied for this hypothesis, that in all those examples where X is from the set of training examples, then hypothesis and the target function's value, they should be same. So when we have this property, then we say that this hypothesis is consistent with a set of training examples, D of target concept C. So the consistent hypothesis means that even if you do not know the target function, at least your hypothesis should satisfy all the training examples. So this consistency with respect to specific D, that's what I mentioned. So mathematically, this property can be, these definitions can be given in this way using that notations. You know that we have used the corresponding notations for expressing the predicates here. So if for all such examples where you have the X, which is an input in the training examples, actually an element of D, and Cx, which is the value of the target function. Actually, the value what is being given, that is the value. So it is already provided you that supervised value. So naturally, the target function's value is known to you. So for all such cases, the value obtained from the hypothesis, that means from the function which is hypothesized, that should be the same with the value obtained from the value given by the target function. So then we say this is consistent. Now, if you get some hypothesis where this property is not satisfied, because there may be some examples where your value would be deviating from target function, there could be various reasons for that. One thing it could be that your training sample is not error free. So which means that you can allow at least for certain fraction of training samples, it may not agree, because if there is error, so you are not absolutely sure that for a true hypothesis whether the equality property should hold, right? So this is that could be one such scenario, or it could be another scenario where you are we are working with a tolerance. Even your training examples values are, I mean, if you consider also it does not have any error, because for the sake of simplifying, your model, sometimes we may allow certain error. Just otherwise, no. So model is so complex that no, it may not be applicable for every possible training examples. But if we can get some model which is largely applicable, that will also serve certain purpose. So this could be another motivation. So it is not always that no, we go for consistent hypothesis. We may go for this kind of approximation, and that is what you will find in most practical cases. That is what we do. But for the sake of our particular understanding, the foundations, we will actually discuss now only for the consistent hypothesis. Now the label, already the name you have seen, that those kind of hypotheses which is not consistent, those are called agnostic hypothesis.
Sir, I have one question.
Yeah.
Yeah, sir. So, sir, go to the previous slide, please.
Yeah.
So, sir, here you told that we are just examine based on the observed training example that we have. So, are we considering that unseen examples or just observed or seen examples for the training?
No, naturally, if it is unseen, you cannot use it. No? So, what is your question? If you are,
My question is
say
that
yeah,
whatever we are building, we have to further use test set.
right. But there you do
yeah.
not know. There you do, no, test set is a different thing. See,
Okay.
test set that is for you, but that is also given to you. That is also part of your training example. Okay. So in that way, so that is for building the model. Just let me take at least a certain pause, and then I will come back. Okay, so is it clear? So in our so far what we are discussing, that we are considering only the hypothesis where training examples are satisfied. That's all. So we are not dividing again between from the training examples, training set, test set. That discussions will come later on.
Hello.
Okay.
Hello, sir.
So now let us consider. I mean, I think we have discussed this also earlier, but we are repeating it. So consistent hypothesis may not be unique, as we have already discussed. There could be some other hypothesis which will also satisfy all these training examples. Most specific hypothesis where the property of most specific hypothesis is that, let me ask you whether you have understood. So, what is the property of most specific hypothesis in terms of, in terms of training example, in terms of the data that we have considered? What is the assumption when we have derived the most specific hypothesis? Can any one of you tell? What is the key assumption?
I think we are considering the positive examples only.
Yeah, why? So what is the assumption? You are right, and we are only using positive examples. That why we are not seeing negative examples in the algorithm? That is, you are talking about in the algorithm. I think naturally when you test consistent hypothesis, we have to test negative samples also. We cannot ignore them. Yes.
I think the assumption is that it's a consistent training set, like there's no error in it.
No, that is so. That is in general, yes. That is one assumption. Yes, that is one assumption. But that is not the key assumption with respect to most specific hypothesis. I mean,
sir,
yeah.
Sir, we are avoiding the situation that the hypothesis does not exist. So that's why we are considering only the positive hypothesis.
That is the outcome. That is the outcome of consistent hypothesis. That is the outcome of a consistent hypothesis, because that is the outcome of this algorithm, Finda's algorithm, that you will get an hypothesis. You will get a hypothesis, and which is the most specific hypothesis. So the contradiction you are not checking, right? That is one assumption. Yes, that is one. There is no contradiction. So if something is positive, we are not in the data, that cannot be a negative, right? That is a contradiction. Or in your generalization also, if you're in your cases, if two literals are positive, so some contradictions will not be allowed. Any other? Yeah, I think the second one also is okay. See, the key assumption, if I can tell you, that in this case, what are the negative samples? So so when you test it, suppose you get the most specific hypothesis. Now, if I give you an input which is not part of the training example, what should be your output?
Zero.
Output will be always negative. I mean, 0 or false, whatever you say. Because that is the assumption that only possible positive examples are in your training set only. All are examples negative. And that gives one consistent description, isn't it? So one contradiction is still there because of generalization. There is no, if you get two attributes which are no, for which is true in that combination, same combination we assume for all other attributes also. For multi valued attributes, we have some issue. Anyway, so that is one limitation of that. But the assumption is that the barring from the positive examples, any other example is negative in your test when you are testing the hypothesis also. That means for unseen cases also. So that is a very strong assumption, but that is what you are considering here. And that no, breaks the consistency part. Only there is a situation when some could be also positive. There is a situation which will not really contradict the negative example. That is a contradiction. But mostly it is that other examples are all negative. So that's why the negative cases you are not considering, because it is only the positive cases are being satisfied with your data. But there could be different ways. So another situation could be, suppose I check only negative examples, and I build up a hypothesis where only negative examples will be negated and rest other samples are positive. In that case, like most specific algorithm, most specific hypothesis, what you will get in that case? See, if I just reverse this technique, where I will check simply the negative examples, okay, and no, I would see that my hypothesis should reject that example only. Accordingly, I will modify. I can come up with an algorithm for that, isn't it? Any question?
We'll start with the most general algorithm and start negating the,
Yes.
like setting
We
the
have
conditions
to,
in order
yeah,
to
we have to
negate the
derive.
examples.
Yeah, we have to derive next more general or to next step of specific to the general algorithm, which will actually will not include the negative example. You are right. In fact, we'll see that actually this is one method. This is a method we are also going to discuss, but in a different context. So that would give you another hypothesis, and which we'll rather call most general hypothesis. So you have most specific hypothesis, most general hypothesis. Now, in between, there are also hypotheses which will have at least satisfy the training examples functional value, and then depending upon the constraints posed on the specific set and general set, you will have you will have some of other conditions. That means partly some of the samples would be unseen samples would be positive and partly would be negative, and they would be consistent with respect to your specific hypothesis and general hypothesis also. So there are various possibilities. I will give you with one example, then I will give an example which will make this thing clear. So version space is the space of or all such consistent hypotheses, or it's a subset of hypothesis from H consistent with T. So any hypothesis in the hypothesis space which is consistent with the set of training examples, that hypothesis will be a member of the version space. Okay, that's the definition. So naturally, this definition you need to require hypothesis space, and so this is what is the set theoretic definition. I hope it is clear to you, because you can see H is an element of the hypothesis space, small h, which is an hypothesis, and capital H is the hypothesis space here. So it has to be an element, and then the other part is that it should be consistent. Oh, somehow I'm not getting pointer pink color. There is some issue. Anyway, okay. So this is the definition. Is there any doubt on this definition?
Sir,
Yeah.
by consistent, do we mean like for both positive and negative training examples, right?
Yeah. Both positive and negative training examples should be satisfied in H. That is the definition of consistent hypothesis. Okay. Fine. So one of the ways
Sir,
you can, yeah.
Sir, in find S algorithm, we consider all the training example positive or both.
No, only positive examples in the find S algorithm. If you
Okay,
are checking every time a positive examples, and then you are going to derive the next stage of generalization of the hypothesis, depending upon so that you should come up with an hypothesis which will satisfy so far whatever positive examples you have seen till that point. Okay.
Okay, sir.
Hello,
And
sir.
it is basically monotonically going to generalize every attribute set, because if you get multi-valued positive set in that positions, so wherever you get multi-valued, you are actually assuming that it should be true for even for other values also. That's the kind of assumption there. So you are upgrading that value with a question mark. The literals will be modified. So that algorithm, please just note it, then you will find it. But we are not examining any negative example there, and that there is a limitation for that also. Now, for each training example, in this list then eliminate algorithm, it's very brute force algorithm, which means if I have a list of all hypotheses, suppose you have, then you simply take one of them and go on checking the consistency property from the training examples, consistency property of the hypothesis from the training example. If it violates, then don't use it, don't include it into your result set. Otherwise, no, you include it. So that is the case here. Okay. Now it's as I mentioned, it's essentially a brute force procedure. So let us once again revisit the find S algorithm, as one of you were mentioning, that once again we can understand how it is doing. So let us not look at the picture right now. Let us go through the training example. So you know that for the find S algorithm, it is the first hypothesis. The starting hypothesis is shown here. What that means, you will start with a point. What is that hypothesis? Every attribute value is null, right? Which means it is the starting point. Most specific is that every sample is not satisfied, which is not really the solutions, but that is the starting point, because you know that that is the most specific part. Everything is a null. Now you get, so because you don't have any training example of that time. So you do not have any training example, it is starting point, your training set is 0. So you assume all hypothesis is null, trivially. So that's why you have taken. Now you have received, you have observed a positive training example. Naturally, H0 cannot satisfy this condition. So you have the first hypothesis. And what should be the first hypothesis?
X1.
Pardon?
Same as the
X1. Same
It's,
X1.
it looks like X1, but it is, that it is a Boolean expression. So difference between X1 and H1 is that X1 is an input. Of course, the label is also shown here. And H1 is a Boolean expression. I hope you have understood the difference, but we are using similar notation. Then you get the you get the same next training example. So what should be how H1 should be modified? So next iteration, what should be your hypothesis, which will satisfy both X1
Sir,
and X2?
the third one is don't care.
Don't care.
Third
Yeah.
one is don't care.
It's don't care, right? Is it clear? Next,
Yes, sir.
we come with the next example, which is a negative example. So what would be your next hypothesis?
Same as H2.
No
Same
change.
Same as H2, so I'm not writing it. I think I have not written it. Oh, no, I have written it also. It is the same. So it should be X4. Don't read it as X3. Your next hypothesis is a positive, next example is a positive example. And what should be your next hypothesis derived from H3? That would
Fourth and
satisfy.
fifth, last two will be question mark.
If we don't care.
Don't care. We have already done this exercise. So you see that this is the hypothesis which satisfies only these positive examples. Which satisfies only these positive examples. Also, there is an extension, like wherever question mark, if there are multi-valued cases, then there are other value also. Multi-valued means more than 2. I'm sorry. Multi-valued means more than 2 valued attributes. The other values may also it shows. So there could be a little bit additional. But if all the attributes are binary values, then the situation is that only those positive examples are satisfied by H4 here. Say only X1, X2, X3 would be satisfied. Rest all other samples, right? Rest all other samples would be negative. I mean, you have those combination. You can see that also. Okay.
Yes, sir.
So that is why you did not look at the negative examples, because there is no need, because you know that this is what is going to satisfy, and this is the consistent hypothesis. But there could be also more general hypothesis than H4. Like if you notice that, so H4 is least general or most specific. If you notice this negative example, anyway, we'll see that. So restriction on most general hypothesis, looking at the negative sample. So just you just look at this, that strong in this case, it is true for all these strong. And if I look at the negative example also, you see that in the negative example, there is an attribute in the first place, that is, I think, sky condition, that is rainy, right? So if I make also strong, don't care, I mean, that attribute which is the third from the end, if I make in place of strong, if I replace it by don't care, I think that would also satisfy all these training examples, isn't it? If I look at the negative example, and because I need to, while generalizing, I need to definitely consider the negative examples. It should not satisfy the negative examples, at least. I mean, that is what I need to know. I need to preserve. So if I make strong, in this case, don't care, in the next hypothesis, suppose another hypothesis, H5, sunny, warm, question mark, question mark, question mark, question mark. Suppose this is one. Do you think that would satisfy all the samples?
Yes.
Yes, sir.
Yes, sir.
So that is also consistent, and that is also general. That is more general than H4, because what is the property of these relationships? How do you set the, when do we say? So let me write it. Say this is H5. So when do we say that H5 is more general than H4? Can you tell me which property it is?
It allows more examples in its.
No. There is a very, I should say, mathematically tight definitions which we discussed.
H5 should satisfy
H5
all
should
the
greater than H4.
That's a symbol you are using. No. You have to,
So the inputs.
So
So the
the
For
inputs
order
every
based on
input,
H,
you
you
have
have
to
to
satisfy
satisfy
the
I think I will ask. I understand there are a lot of people who know.
order of
Sir,
H5
H4 is a
should be.
subset of H5.
What does
So
it
it
mean?
would be like
I mean,
whenever
H5 is
again,
more
H4
general than
takes
H4.
the
no.
value 1,
See, these
H4
are all
would
tautology. I
implicitly
mean, you
take
are
the
saying the
value
same
as
thing.
1.
Sir, H4 implies H5.
No. Again, that definition is not, no. It will not be accepted. Huh? You have
Sir,
to.
it's a subset.
But for every training example, H4 and H5 give
For
the
each
same
X,
positive
sir, if
output.
H,
Sir, for all x, if
so it would be
H4x
like
equal
for
to 1
each X,
implies
if
H5x equal to
H4X.
1.
Yeah,
What
right.
about 0? Are you not saying that for 0 it can imply anything? Are you saying that for 0 it can imply anything? So why are you saying for H4x equal to 1, then H5x should be equal to 1?
so that if any instance H4 is giving 0, then H5 may give 0 or 1.
May give 0 or 1.
Because it's
Therefore,
a,
it is not consistent, na?
yes,
See,
sir.
while deriving H5, I made sure that at least it should not satisfy the negative example. That is what I discussed, and that's why I have checked that H4 contains sunny, and that's why and X3, sorry, that example X3 and negative example X3, it has a rainy. So if I make that attribute don't care. So since it contains sunny, so X3 is not going to be satisfied. So I made sure that. Then only I said no, H5 is also a consistent hypothesis. So you have to consider that also. So please look at the definitions of generalization. I mean, when we said general things. So let me come to this definition once again. So these are mathematical definitions, and you have to learn to express this mathematical form. Sorry, I just yeah. You see, oh, it is equal to 1. Actually, only positive examples, but negative examples also it should satisfy. I think there is some problem.
for negative, it should become opposite.
Just like if it satisfies both positive and negative, then what is the difference between the hypotheses?
Huh?
If it satisfies both positive and negative, like if it does it for both of those cases, then what is the difference between these two hypotheses?
Oh, acha, yes. You are right. Yes. Yeah, I'm sorry. So because most specific hypotheses So it has to be consistent also. More general, so the h prime x equals 1 and hx equals 1, yes, right. And then the negative examples could be also positive, but we want it is basically in a sense more general, but we want more general consistent hypothesis. So at least for the training examples, it has to satisfy. So there are two things. One is more general, another is more general consistent. Okay. So there is the doubt. Because otherwise, no, we should not have looked into negative examples also.
Sir, as there is more general, we can similarly define more specific, so we can take the intersection between them.
No, it's just the opposite definition, but no, we just go by this more general definition. So let me explain what I meant. Say, the question here is that when we are getting more general, in this case, we are actually obtaining more general consistent hypothesis. So that qualifier also you should understand. So consistent, that's why there are negative examples in the training set. So I should say, I should change that definition. First thing is that whatever positive, see, with respect to training set only we are defining here. So for the, with respect to the functional definitions, whole functional definitions, wherever it is positive, that H4, H5 should be also positive. For H4, whatever is positive, H5 should be also positive in the whole input domain, right? But for consistency, for H4, wherever it is negative, in the training example, H5 also should be negative for those cases. That is another constraint, which is not really, specified in that more general definition. It is more general consistent hypothesis. But it could be any other negative example, other negative values in that domain, which is not part of the training example in the input space. Their H5 could be either positive or negative. That is right.
Sir, if you take H6, if you take another H6 and make warm also don't care, like Sunny and 5 don't care, is it more general than H6?
Yeah, that could be more general. Yes.
And it is also consistent.
It is also consistent. Yes, you are right. I have not told this is the only thing. You should check only that. If it satisfies this part, consistency part, and also that part, that no, wherever it is positive. See, now that is with respect to H5, right? And another thing we have to check that no, the whole thing, that is the most specific to most positive part, should satisfy, right? Sir? So these are what you have told. Actually, you see that it is also written like this.
Excuse me, sir. Could you please move to the previous slide?
Yeah.
I had one doubt in that. So, if we consider sunny, warm, don't care, and then instead of strong, if we consider another attribute and another don't care to last two. So it will be negative for H4, but it will be positive for H5, right?
It will be negative for
H4, but it will be positive for H5, right?
Yeah, definitely.
So you said that if it is negative for H4, it should also be negative for H5.
In the training example set. And also wherever it is positive, it should be also positive in the whole input space. That is a general definition. More general.
If we consider a training example called X5, which I mentioned earlier, so X5, if it is negative in the training example set, so it will be negative for H4, but it will be positive for H5, right?
I'm sorry. So in the training, what should be the training example? Can you tell me? I cannot write it. I have some issue with the pen. But you tell me.
So if X5 is sunny, warm, don't care, and instead
No,
of
no,
strong
X5 cannot be in that form. See, X5 is an input point. In the input space, you don't have don't care value. Don't care is a Boolean, a literal for the Boolean expression. In the input space, it has to be always some point.
Yes, sir. So instead of don't care, we can take any value.
It takes some value. It takes some value.
Yeah. So sunny, warm, high, and instead of strong, we can take some other attribute. I don't exactly remember it.
Right. So weak, for example.
Okay. So weak, and then warm and same, right? And if x5 is negative, so till h4 it will be the same hypothesis, but h4 will be negative for x5, and h5 will be positive for x5, right?
So then H5 cannot be more general consistent hypothesis, most general consistent hypothesis.
So it will be more general, but it won't be consistent, right?
Yes, that is what I'm trying to stress. Yes.
Okay, sir, got it.
So we want in a version space only consistent hypothesis. In a version space, we want consistent hypothesis, and there is a order for that. There is also an order for generalizations. Okay,
Sir,
among the
then,
consistent hypothesis only.
sir, then find-S algorithm may not find a consistent hypothesis.
Yeah, find-S algorithm has an issue for that. Yes, there could be a contradiction. The assumption is that you have a consistent hypothesis. I mean, there is no contradiction. Yes, find-S algorithm has limitation. But assumption first, key assumption is that only positive examples are looked at, and assuming all other examples are negative, except now some generalization cases. I told you some of the multi more than two valued attribute cases. There is some issue. Right. So this for this particular example, you get a version space like this, and it also shows the corresponding generalization relationships. But this is among the consistent hypothesis. Okay. So actually, the other approach, see, we have discussed about the exhaustive approach, where you examine every possible hypothesis in the hypothesis space and check whether it is consistent or not, and then you take it as your output. So you get set of all consistent hypotheses. But instead, if we can, if we can compute, because there is a, we'll see there is a property by which we can say that in a version space, there would be a set of most general specific hypotheses, and also there would be a set of most general hypotheses. In this case, they are denoted by S and G. Then all other hypotheses in the consistent in the version space will have these relationships, that they are more general with respect to a hypothesis in the set S, and they are more specific, if I say in the other way, with respect to an hypothesis in G. Now, this is the property which we can just a minute. Which actually gives us this kind of ordering. So there is a theorem for that. We are going to discuss that also. Now, these are the things I have already mentioned, that these are the two properties of these things. Right. So that's why we can have a compact representation of the version space utilizing that property. So it's a kind of lattice structure where you have a set of hypotheses which contains the most specific hypothesis, and a set of hypotheses which contain most general hypothesis, and those are the boundary sets. And any other member within will have the property that it would be more general to that most specific one, and the other one. So this is what generalized from most specific boundaries, and we use positive examples. Specialized from most general boundaries, we use negative examples. This is the computation. We'll see that algorithms later on, and generate all intermediate H's in the version space. So it is sufficient if you have these two sets to get all other hypotheses in the version space. So these are the two boundaries in the version space. They are actually set of consistent hypotheses, And as I mentioned, the that element of that set, the general boundary, it is the set of its maximally general members consistent with the training example set D. And the specific boundary S is the set of its maximally specific members consistent with the training example D. So while computing it, deriving it, we summarize the negative examples, and also so anything more general covers strongly a negative training example. So you think the other operations from the other end, as one of you have mentioned already, we can start with all don't care, and then we iterate by rejecting the negative examples by modifying the hypothesis so that it can reject the new negative examples what is appeared in that sequence, what has appeared in that sequence. The way we did specific most specific hypothesis, that computations, you think from that angle. Similarly, we compute also from the other side, we compute the iterate the specific boundary. The one extra task we have to do, because we have not checked the negative examples in that case, but whenever we are updating the general boundary, we should see that at least there should be some hypothesis which is more specific to it with one of its hypotheses. If there is a contradiction, we cannot include it. So which means there are certain negative examples which are not satisfied. It will not be consistent. So for the consistent part, it has to preserve the whole functional values. I mean, for the training examples, it has to preserve that property. For within that D, one value of a hypothesis, specific hypothesis H has, the same functional value should have also for the more general hypothesis. So this additional constraint you need to consider with respect to this version space. So this is what now in the version space this is a theorem which says that there is an order. There are two elements where you can they act like a boundary element, or upper bound, lower bound in the case of lattice structure. So you can see that the definition here, the statement of the theorem is that it is equivalent. If you have a set of hypotheses in the hypothesis space such that that hypothesis is more specific to one of the hypotheses of the of the set S, and more general to one of the hypotheses of the set G. The other way, more general from S and more specific for G, then that hypothesis will be included in the version space. So that is your description of the right-hand side. On the other hand, left-hand side says that only those hypotheses, they will form the version space. There is no other hypothesis in your hypothesis space which will be outside of this property, which will not satisfy this property. So that is a very key theorem, but for which actually you have this compact representation. The proof is a bit straightforward. I'm just giving you the sketch. You need to go through that book, and you will find almost whatever I'm discussing, it will be there. So as you see that you have to prove from the both ways. You have to prove that first thing that if something is satisfied, if the right-hand side is satisfied for a hypothesis, assuming S, naturally the definition of S means all the hypotheses in S are consistent, and the definition of G means all the hypotheses in G are consistent, right? Then you have to show that H is also consistent if this relationship holds. That means G is more general to H and H is more general to S. Directly from the definition itself it comes. You can check that. On the other hand, as you say that, as I am saying, that every member of version space should satisfy RHS, which means every consistent hypothesis, version space, that's the definition, that every hypothesis has to be consistent. That is the minimum. That is the basic definition of the version space. So, which means any hypothesis which is consistent with respect to the training examples, that is good enough. I mean, that should be also element that should satisfy this property. That property which has been mentioned, that should be more specific to a hypothesis of the general boundary, and more general to the hypothesis at the specific boundary. So the first thing I just mentioned, that it is coming from the definition itself because of the consistent hypothesis definition. And once again, that's from the definition. H satisfies all positive T's, but no negative T's. So H should be H should be. I mean, it is consistent. That's why. So H should be more general to S because it can satisfy. So from the general definition, H is general to S because it satisfies all positive examples, and as you have said, that is good enough for defining the general definitions. Similarly, for G, again the same thing, that for G all positive examples are satisfied, and the negative examples we don't care. So that's why G should be more general, because whatever H's positive examples are there, that should be satisfied with respect to G. Okay. So from there, we come to this particular algorithm, the approach. That means, as I was mentioning you, that if I look at the positive examples, we'll modify the boundary S, and if we look at the negative examples, we'll modify the boundary G. So that is what, if D is positive, you should remove G every hypothesis inconsistent with D. Now that's a regular checkup. Usually, no, for G, you are satisfying that your assumption is that all negative examples that should be rejected, but you are not, you assume all other examples, all other positive examples should be true, right? So now if you get a positive example, so naturally it happens that if that positive example is not satisfied with respect to G, so that hypothesis needs to be removed. That hypothesis needs to be removed, that's all. But if you get a negative example and it is getting satisfied with respect to G, sorry, it is since it is positive, so naturally you have to iterate, if you have to update the S with respect to your present, some hypothesis where D is not satisfied. I mean, every hypothesis has to be inconsistent. So if there is any hypothesis which is inconsistent, then this needs to be generalized. So it is removed and you have to make the minimum generalization, the way we did for the find S algorithm. And also you should see that some member of G is more general than H. Okay, and remove from S every hypothesis that is more general than another hypothesis. So in the S itself, there should not be that relationship. So there should not be any hypothesis which is less general. So if the negative sample, you do the other way. As I was mentioning here, you have to check that any hypothesis in the G which is not rejecting that sample. That means it becomes inconsistent. Then you have to do the minimum specializations. That is the opposite operations. And again, you keep check on your S boundary. So just summarize that only positive samples, training examples are used for generalization of S, and negative for specialization of G. And you check on the elements of both the sets just to see the consistency of your that generalization relationships should be there. So the advantage here is that first thing, the convergence is guaranteed if no errors, and there is H in the hypothesis space describing C, which means if you can get also contradictory state, and you may get null set in the Gaussian space. So this is an example that you start with from the specific boundary. So the element would be all null. I mean, because you do not have any training example yet. I mean, you have not checked any training example yet. And similarly, your general boundaries, all your laterals should be don't cares. So suppose you get the sunny, warm, normal, strong, warm, same, right? So what should be your next stage of S1 and G1 if I say, because it's a positive example. So how they should be modified?
So we will specify S1.
S1
S1 will be the same as the training example.
So it means that literal, yeah, sunny, warm, this will become. So you will get this, and naturally G1, you don't. I mean, there is no contradictions. I mean, it is satisfying that example. So you don't have to do anything. Huh? It is satisfying that example. So next part is also positive, right? So what should be S2?
Don't care in third position.
Don't care at that third position.
Right. So still G2 remains same. Okay. So you come with the negative example. So how G2 would be modified? Because now the G2 would be modified, and you should also check in the S2 whether it is getting satisfied. It is not. It is getting rejected in S2 also. So it is okay for S2. But G2, as you see that it is accepted in G2. So the G3 should be modified. So how G3 should be modified?
It will be totally
suppose
opposite.
we can take
You
sunny
have
and
to
all
take
don't
the
care.
minimal specializations. You should note that there are many possibilities, but it is a minimal. That means it should accept as many as samples. Only this one should be rejected. Suppose only this one should. That is what is the most general thing. And all other samples are accepted, which are accepted in S2 also.
At least one of them attribute should not match to that of this.
So third one should be just high in G2.
Third one
should become high in G2.
Should become high in G2.
No, sir, it should be changed to
Sir,
low.
sir,
Sir,
first one should be sunny, and after that all will be don't care.
Sir, each attribute will be specified at most. Means exactly one attribute will be specified in G1 and in G.
Yeah, you just give example. What does it mean?
Like without any there is sunny, and all five are don't care.
Is there any other possibilities?
Yes, sir.
Yes, sir.
There is without means the warm, and then
And
all
all
other don't care. Like each attribute will be
No, you just tell
specified.
me. So which means warm. Okay. Can it
Yes,
be
sir.
cold? Cold all other?
No, sir. Except cold. Except cold, we will put all the values, and all others are don't care, because the cold is a negative example in the here.
Can it be sunny, cold, all other?
But sir, it is means it the more general is sunny, and
More general is sunny. Yes,
yeah.
yes. I'm just asking you. Yes. So you are saying sunny, all don't care. Then
Yes,
don't care, warm, and all don't care. That is one.
Yes.
Any other possibilities?
Yes, sir. Without high,
Yes,
all
sir.
the values which are possible there, and all five are don't care in the
Without-
third attribute.
Sorry,
Except
without-
high. Except high.
High.
I don't remember actually the values in the third attribute. There
Say
can be some
high, low. Suppose say
yeah.
low.
So low, and all five attributes will be don't care.
That
The
would be
values-
the next case.
Yes, sir.
Low, all.
Five are don't care.
But in that case, will it be more general to S2?
No, sir.
No,
No,
sir.
sir. It will reject the ones which are high.
Yeah. So it should not be then. It should not be considered. So we have to consider that also.
I think
Sir, then
we can.
So that should not come. That should
Yes,
not.
sir.
Then
Yes, sir. Then in the fourth one, there can be some values apart from strong, except
apart
strong.
from strong,
Only
we
the
will-
last, first, second, and last one can be changed.
Say strong. There is a value called weak.
Yes, sir. Then okay.
But we cannot put weak because the S2 has strong in it, so it has to satisfy strong.
Only
Not,
first, second,
cannot
and
be
fifth
more
one
general
can
than
change.
that.
So you have an issue there. You cannot put that.
Rain, cold, or warm. Last one change.
What about same and change? What is happening there?
You can put
Sir, sir, we cannot put anything for that also. No, sir. Sir, it
What
can be
about
say.
the fifth position worm?
Sir,
What about the fifth position worm?
Don't care.
Sir, it
The
can't be
fifth position,
anything.
there are two worms, huh? There are two attributes. Huh?
Yes, sir.
The fifth position worm, if I put worm and all don't care,
No, sir. It will.
Then Reni will be a problem, no?
Sir, the negative example will be satisfied then.
Yeah, negative examples will be satisfied. Okay, let us see.
Sir, in the fifth position, we can put.
See, we have missed this same. See, you have told first to write, but we have missed same. Because negative the change is not required. No? Change is, so if I put all don't care and same, they are satisfying, isn't it? They are also minimum generalization.
Yes, sir.
Okay. So S3 is this, as you know, as you understand that it is a negative example. So S3 is not going to change much unless it contradicts with respect to that. So let us then go to the next example. Okay, this we have discussed, so let us not put that thing. So the next example is sunny, warm, high, strong, cool, change. It's a positive example. So how these boundaries are going to be changed?
Last two will be
Last
in
two will
S3.
be
Last
changed
two
in
will become
S3.
don't care.
First thing, which one? Last one will be
Last two.
Last two.
Sir, the
last one will not be satisfied, isn't it? So last
Yes, sir.
last case has to be removed from G3.
Yes,
right?
sir.
What about
Yes,
S3? What should you do in S3?
The last two
Last
should
two
be
will be don't care.
Last two will be modified.
Last two will be modified. Okay. Right? So this is S4, this is G.
The same.
In fact, that is what we obtained. Na? I mean, these are the 4 examples, and this is the version space. If you look at the diagram, in fact, that was the result I was showing you. Yes. Now you come back to this. Huh? So you will see that these are the 2 boundaries, and also there are some general cases, more general cases than S, and also more specific cases than G. From G also, you can have this. You can compute them, though you are not explicitly computing them, but you can derive them. In your algorithm, you are not computing them, but from your representation, you can get them. So that is the compact form of representation. You need not represent them, but it will represent the whole version space. You can get any other hypothesis which are not mentioned here, which are in between them. That also you can get. So please go through the book once again, as I mentioned, and in fact, tomorrow there is no class. Again, next week we'll be having our lectures from Wednesday, and you should, again, for this week also, you have to fill up that form, weekly report, that you should do. First, let me take your attendance, because already my time is over almost. So let me download the attendance. I hope it is downloaded. Okay, so if you have any questions, I can take a quick questions, because no, you have some.
Sir, for report, we can consider only that class, or we can also write something from previous classes?
No. Only for that week. That week, whatever, it should be 1 page. It should not be more than that.
Okay.
I mean, it is like that only, and there are certain points. Only for that week only. Don't write different things. Whatever we are covering in the class, it should be reported from the class. I mean, whatever you have understood, you have attended the class, put those things.
Okay.
Sir, would it be possible for you
Sir,
to
can I-
review 1 or 2 documents?
Sorry?
Can you review just 1 or 2 documents and tell us like this format is correct and this format is not?
No, we don't do those things. I mean, you please do as per your understanding. I mean, we have already given enough structure in that document. You answered them. That will be fine. Okay.
Sir,
yeah.
So can I refer the previous classes for compare to this lesson? in the
I
weekly
mean,
report?
see, if it is absolutely essential, you are giving your comments, etc., please do it, because there are certain feedback we want. So with respect to that, you do it. But not with respect to topic. You
which
concentrate on the topic what we have covered.
book we should refer?
I have already mentioned, right? It's Tom
Sir,
Mitchell.
which book we should refer to?
Tom Mitchell's. You go through my first slide, first slide set, what I have already uploaded in Moodle. Please download it, and you will find out some books are, I have given some names of some books. There you will see that there is a book by Tom Mitchell. Okay. So that book, whatever I'm covering from that book, and that book is very good, and it is available in low priced edition also, and I mean Indian edition. So I would suggest that you should get that book and read it.
Excuse me, sir.
Yeah.
Sir, I just had a small request. So, will it be possible for you to take some of the questions raised by the students at the end of the class? Because
no,
I think
it's not possible. It is not possible. See, it has to be interactive.
Okay, sir.
It has to be. See, the speed will be determined by your ways of interaction. I agree. I understand some difficulties with this mode of interaction, but because the students have questions, some doubts will be there. Unless I feel that it is not possible to remove the doubt for that student because of many other things, I will try to adjust as much as possible, accommodate the query as much as possible.
All right, sir.
Okay.
All right, sir. Thank you.
So in the weekly report, can you just tell us
Pardon?
what do you mean by novel idea?
Novel idea.
Yeah, last part of the weekly report, like just.
Do you have any? Yeah, that is your imagination. So after going through this lecture, do you feel something? No, some interesting thing you can do, or you can apply it to do some interesting thing. It is nothing. No, you are asked to do. Just your. So when you are reading something and if you are excited on certain things after learning, whether you have understood it fully or not, no, you feel no. So this is the thing you can do. This could be applied here.
So can it be also like if we find like if something concept could be done in another way, like to get a better algo, like for us something like that, or it should be like a practical approach only?
Yeah, but don't write essays and paras. No? We don't want that. Only key idea that should be
Sir,
not more than one or two
sentences. But it could be like
explain.
on something on concept also, right, sir?
Yeah, it is just the key, your approach. I mean, just the concept you should write. So pointer. It is not that you have to describe fully, elaborate fully, right?
Okay.
So your idea, you felt that approach you should write that instead of this, it could be this, or this could be applied in this particular area, and because you feel so. One or two sentences you can write.
Okay, sir.
Okay then. Okay. So thanks, and again in the next class we'll meet on Wednesday. Okay. Bye.
Thank you, sir.